These notes are continuation. We're going to be talking about free body diagram. So a free body diagram, or FBD, is just a picture used to solve problems that involve forces. So we kind of already had an example number one. That was the basic one where we just use F equals ma. But here we have a raft that is free to move on the surface of the water. There's an upward buoyant force equal to the magnitude of the force of gravity, which is 1,225 newtons down. There's a force of 150 newtons east from the strong winds and 250 newtons east from the current. Draw an FBD of the raft and then find the net force and acceleration. Okay, so first, whenever we're drawing these free body diagrams, you'll want it to draw like either a rectangle, a square, or a circle that's going to represent our object. Here we have the object pictured for us. You could draw the image if you wanted to, but primarily we're looking for either the square, rectangle, or circle. So we're also going to include the mass of the object within that shape, so the rectangle, square, circle, just to keep that all in one place. Okay, so if we're going to start with this problem, we have to draw in the arrows that represent the vectors for this. So we will keep to the convention that up is north, east. Okay, these are going to be our positive directions. Okay, so if we have on the surface of the water, there's an upward buoyant force, okay, and a downward force due to gravity. Okay, and they're each 1,225 newtons. Okay, this one, the force of gravity is going to be 1,225 newtons. Okay, and then we have from the wind, we have a force of 150 newtons. And then we have a current in the same direction of 215 newtons. Okay, so now that we have set up all of the vectors in the appropriate directions, for most questions, this will be up, down, left, or right. We generally choose to use the standard reference where up is north, right is east. Okay, so we kind of already set that up. Okay, some important things to note. You're only going to draw the forces that are acting upon the object. Okay, so we don't include any forces the object's exerting on other objects. So this boat would be exerting force on the water, but we're only concerned about the forces acting upon the boat, okay, or the raft. So multiple forces in the same direction are drawn next to each other. If a force is acting down on an object, we draw this force below the shape. Okay, so here we had gravity working downward on the object, and so the arrow was put below it. Okay, we are not going to have an arrow pointing towards the object. Okay, the arrows are always pointing away. Okay, force vectors will always point, like I said, away from the object. And so the length of force vectors are related to their strength. That is that a larger force will have a longer vector. Okay, and so you'll see that up here I have that 150 was shorter than the 215, and I tried to make my two arrows going up and down because they're equal. As far as magnitude, they're approximately the same size. Okay, so it's not vastly important that you make sure that your arrows are, the different sizes. but just make sure that you know that they are going to be different sizes based on their magnitude. Continuing on with this problem, we were asked to find the net force. So the net force equation is just going to be adding up all of the different forces. So when we do this, we need to consider both the horizontal and vertical components separately, then add them using vector addition if needed. Okay, so once again, we have our north as positive and our east as positive directions. Okay, so first we'll start with the horizontal aspect, or the x. So the net force in the x direction would be our force of the current and the force of the wind. So we had 150 for the wind plus our current. Okay, and they're both positive because they were both in the east direction. So we will get a net force in the x direction of 365 newtons, and it is to the east. Okay, now we need to consider the horizontal. So the net force in the y aspect would be our buoyant force and our gravitational force. Those were the two forces working in the vertical aspect. Okay, so our buoyant force was 1,225 newtons. Okay, and it would be minus, because gravity is working downwards, 1,225 newtons for the gravitational. Okay, so our net force in the y is going to be 0. Okay, and so since basically the vertical components cancel each other out, we can kind of just ignore them. So our net force is going to be this 365 north, or 365 newtons east. Okay, so now the last thing we need to do is find the acceleration of the object. Okay, using the mass. So if we look back, our mass was 125 kilograms. All right, so using the formula, A acceleration equals the net force divided by mass. Okay, so our net force that we calculated was 365 newtons east, divided by our mass, which was 125 kilograms. And when we divide this out, we get an acceleration of 2.92 meters per second squared, and that is to the east direction. For more complicated examples, this requires vector addition to find the net force and acceleration. So for example 3, we have a 19 kilogram sled. It's being pulled on ice by two siblings, each holding a rope. The younger sibling pulls with a force of 17 newtons east, 15 degrees north, and the elder sibling pulls with a force of 21 newtons east, 12 degrees south. Find the net force and acceleration of the sled, assuming no friction on the ice. Okay, so the first thing we need to do is draw the free body diagram. So we're going to have our box. Okay, that is our sled. So if you want to draw a sled, you can. There's my brilliant sled. So it has a mass of 19 kilograms. Okay, and then we'll kind of label each of these. So this will be our first force by the younger sibling, and then we will have this as our second force for the older sibling. So the younger sibling is going to be doing from the eastern border 15 degrees north Okay, so that's here. They were pulling 17 newtons. Okay, and then for the older sibling, they are pulling from the eastern border 12 degrees south. Okay, and my stuff is not to scale, but it's mostly important that you put the items that you need in order. Okay, and that was 21 newtons. Okay, so just make sure that you label everything properly. It's okay if it's not all to scale. Okay, and then once again, we will set that our north is positive and our east is positive. Okay, so the things we want to know is what's the net force and what is the acceleration. So first, we kind of have to go through the component method. Okay, so we're breaking it up into the x and the y. Okay, for each of the different forces. Okay, so remember the purple one is going to be our F of 1, the green, let me make this slightly darker green actually, is going to be our F of 2, just so it's easier to see. Okay, so for the x component, to find for the younger sibling, the force of 1x, or the force in the horizontal aspect, is going to be 17 times the cosine of 15. Right, so that I just rearranged that. That's exactly what we were doing before. So it would have been cosine of 15 equals force divided by 17. Okay, so that is basically this aspect right here, this line. Okay, and then for the y, it'll be this line. So we're doing SOHCAHTOA just like we did previously. Okay, and then for the second force, that's going to be equal to 21 times the cosine of the angle 12 degrees. Okay, and then so we're going to add those together. And then for the y side of it, for the first, it's going to be 17 times the sine of 15 degrees. And then for the f2 of y, that's going to be 21 times the sine of our angle, which is 12 degrees. Okay, so all I was doing was I was breaking down these two arrows. So we have this arrow, okay, and so I needed to know this. This is my f1 of x, and then this is my f1 of y. Okay, and then I broke down the other triangle. So if this is my arrow, it was 21 newtons, and the angle was 12 degrees. Okay, I wanted to know this was my f2 of x, and then this was my f2 of y. Okay, so I kind of went through that pretty quickly because it's kind of a review of what we were doing before. But I did just kind of want to touch on that briefly. Okay, so when we add these together, so we solve 17 times cosine, or cosine of 15 degrees times 17, we would get that value, plus cosine of 12 degrees times 21, we would add that value to the previous value, and we will get a net x value of 36.96 newtons. Okay, and then same thing, adding these together. Okay, one thing to note here is that for f2 of y, I kind of forgot to put this, we will have negative here. Okay, so this will be a negative number because it is going south. Okay, So when we add these together, and in fact we'll be subtracting them, we'll get that our net force in the y direction is going to be 0.0338 newtons. Okay, so now in order to find the resulting net force for this, we will have to draw a triangle and use Pythagorean theorem and then use the inverse tangent to find the angle. Okay, so drawing the arrow, or drawing the triangle, sorry, our x is going to be 36.96. Our y is going to be, and actually I put that on the wrong side. Oops. So our x is 36.96. Our y, and this is not to scale, is going to be 0.0338. And so we want to know what is the resulting vector. This will be our net force, or total net force. Okay, so Pythagorean theorem, we will take the net force squared equals our a squared plus b squared, so 36.96 squared plus 0.0338 squared. Okay, and when we go through and solve it, we'll get that the net force, the total net force, is 36.96 newtons. Okay, so you'll notice that it is very close to what our horizontal force is. It's the exact same here based on the rounding. And that's just because the amount that it is getting pulled to the north is so minuscule. Okay, so then to find the angle at which it is being pulled that way, we're going to take the tangent of theta equals opposite over adjacent, so 0.0338 divided by 36.96. Okay, so rearrange, it'll be theta equals the inverse tangent of the 0.0338 over 36.96. And we'll get that our angle is 0.052. Okay. So whenever we go to write out the final answer for this, it would be that it is, I'm just going to round it, it's going to be 37 newtons. And from the eastern quarter, it's going to be 0.052 degrees north. Okay. So now that we have the total force, we can now find the acceleration. So for acceleration, I kind of ran out of room. For acceleration, it's F, or force, net force, divided by mass. Okay, so our net force that we calculated was 36.96 divided by our mass, which was 19 kilograms. So when we divide that out, our acceleration is going to be 1.94 meters per second squared, and it's going to be in the same direction of the final net force. So it's going to be accelerating east 0.052 degrees north. Okay, Also, just a note, you can also solve this by doing, by like adding it via the two vectors using the cosine law and sine law. I know that some of you kind of struggled with that before. That method can get kind of tricky because you have to really know your geometry rules in order to solve it that way, okay? But you can have the option of doing it that way. This way is a little bit easier to make sure you don't make mistakes just because it's breaking it down into the different components.